I'm so happy to have Helen Degeling with us today. Since Helen has had an extensive career as an exploration geologist and exploration manager for explorers, producers, and the Director of Minerals Geoscience for the Geological Survey of Queensland. And since May this year, she's the Project Acquisition Manager for Cobalt Blue. And I am super excited that she'll be chatting about her work on Cobalt Blue's Waste Streams project, about battery metals from mine waste and Australia's green opportunity. So this is going to be an awesome session. Please use the chat and we'll open up the floor at the end. And thank you so much, Helen, for joining. I love having you here.
Thanks for asking me back. Yes, I'm excited to be here as well. Awesome. So I think this is my third time on GeoHug, which is pretty cool, and just love that, all these things that we started in COVID are still going and part of our everyday life now. Anyway, so as Jess said, I'm especially excited to be here in my new role with Cobalt Blue, and I'm going to tell you all about our critical minerals in mine waste project, which we are aiming to set up globally. So by the time I'm finished, I hope that you will all come away with a strong sense of opportunity that exists here in Australia and around the world for reprocessing mine waste, such as tailings, but there's other types of waste as well, for critical mineral value, but also at the same time getting better environmental outcomes for those sites. So let's keep going if my computer wants to work. There is a little disclaimer. You can read that whenever you feel like it. Now, I'm pretty sure that everybody knows this sort of information already, but I am going to set up the framing, and if you just bear with me while we talk about all the different metals that we need for the energy transition. Does require, of course, the widespread adoption of cleaner and greener technologies by which our society can obtain the electricity that we need in all aspects of our lives. However, whilst those energy solutions may in themselves emit far less carbon dioxide than fossil fuel energy generation, they are actually far more metals intensive than those traditional energy generation methods. So these graphs are from the International Energy Agency, and they show the amount of metal required for green energy solutions compared with traditional fossil fuel-based technologies. So on the left, graph on the left shows a typical electric vehicle, EV, compared with a more conventional ICE car, internal combustion engine. And the bottom axis of that graph shows kilograms per vehicle of different metals. So you can see that the EV requires so much more metal than the conventional combustion engine car, and it's all of the energy solutions and energy applications need copper, because that's how we transmit and move electricity around. But the batteries, the frame of the car, the way the whole thing is set up requires a huge amount of other metals that we've just not really used a lot of in the past, and now, of course, we don't have enough. So same thing on the right is a comparison of different energy generation options, including offshore wind, onshore wind, solar, nuclear, and then, of course, coal and natural gas down the bottom comparison. And so this graph shows the kilograms of metal required per megawatt of power being generated. And again, you can see that, wind just requires so much more metal per megawatt than natural gas or coal. All of them need copper, but the amounts are just so much bigger. And then you throw in the different things to actually make that technology and get it to work effectively. So how we achieve the energy transition whilst maintaining all of the environmental, societal and climate goals that we desire and that are important to us, I think is the challenge of today's mining, metals and manufacturing industries. We also know that even with the best of intentions, we can't reach these metal demands through recycling alone. So we do need new mines and new sources of these metals, but we don't really want to start just mining frantically, holers bolers all over the place and abandoning our strong environmental practices for the sake of mining as much as we can, as quickly as we can. So instead, I'm hoping that today I can show you how we can be far more efficient with the mines and the deposits that we already have. Right, so this is a graph that was produced by the International Council on Mining and Metals, ICMM, in 2022. It shows the breakdown of tailings volumes produced by key commodity streams. So we've got alumina, we've got gold, coal, iron ore, nickel, and the largest one is copper. According to this study, 3.4 billion tonnes of tailings was produced annually in 2019 from copper mines alone. If you add in nickel, we're up to about 5.5 billion tonnes per year of tailings production. The graph also shows the increase in tailings production over time from 2010 to 2018. And we see that happens because of globally declining grades, first of all, of the biggest deposits. So we need to dig up more in order to get the same amount of metal. And that's weighed against then increasing demand, which is driven largely by the need for copper and nickel in the energy transition. So the volume of tailings produced per tonne of metal is only increasing. And this data, this graph, is already 4 or 5 years old. So the total here of about 9.5 billion tonnes across those 6 commodities is actually only now going to be a massive underestimate. We also know that nature doesn't make things 100% pure, and there are other commodities mixed in with the original ore of these copper, nickel, and other mines. Commodities such as cobalt. So in many cases, the coexisting commodities are not, or they were not previously of interest to the incumbent miner. So the people that did the original mining were not interested in the metals that are now so important to us. And so they have, over time, ended up in the waste. So the idea of the work that I'm focused on, and many others, of course, is to reframe this huge environmental burden into an opportunity for green battery metal production for the energy transition. That is the global scene setting. What have we got here in Australia in particular? We have a very active and very proud mining history. We have huge natural mineral endowment. We're very lucky that way. And mining is a very significant part of our economy. This map on the screen is from Geoscience Australia, from the Atlas of Mine Waste portal, which was released, I think, in about May this year. And it shows the mine waste sites that we actually have data for thus far. And it's mine waste associated with both operating and historical mines. So for some sites, that might be a tailings dam. For others, it might be spent heap leach. But yet more, it might be, a low-grade stockpile, some other kind of just, storage pile or dump. These sites might have been rehabilitated. They might, as part of an ongoing operation, they may not yet have been rehabilitated, but whatever the case, they're going to require ongoing environmental management in many cases. Chances are that there is still significant metal and other raw material value remaining in those waste stockpiles. This map shows about 1,500 individual mine waste sites. However, we actually know that this is a significant underestimate because we haven't got a lot of the data that we need, and the number should actually be more likely around double that, if not more. When I was talking to the guys at Geoscience Australia a little while ago, they conservatively estimated that there are approximately 3,500 mine waste sites across all commodities Australia-wide. So that is a lot. Message, I think, is that we can be smarter with that waste. We can look at ways of turning this massive liability into something more valuable, which of course then brings mining activity into the circular economy, which there is no waste and all materials are viewed as having value. Cobalt is obviously a focus for us at Cobalt Blue, but the opportunities are broader than that. There are many other valuable metals and raw materials that also occur in waste, and that might include sulphur from pyrite, for example. And I have a specific reason for mentioning that, because at Cobalt Blue, we recognise the huge potential for cobaltian pyrite in the world's large copper and nickel deposits. The majority of that pyrite has ended up in waste stockpiles and tailings dams because it's too difficult to process. And historically, before the energy transition became important to society, the demand for that metal just wasn't there. We also know that pyrite in tailings is one of the world's major sources of acid mine drainage associated with mining operations. So getting that pyrite out and turning it into useful products has not only economic value, but very, very strong environmental, positive environmental outcomes as well. So with all of that kind of background and scene setting, I would now like to talk a little bit about Cobalt Blue. We're an Australian company with a cobaltian pyrite deposit in New South Wales, which we call the Broken Hill Cobalt Project. And we're developing a cobalt and nickel sulphate refinery in Western Australia, in Kwinana. So the Broken Hill Cobalt Project in New South Wales is currently undergoing DFS to secure finance, and it will produce a mixed hydroxide precipitate from the cobaltian pyrite ore body. That material will then be fed to the nickel and cobalt refinery in Kwinana, which will also be able to take material from other sites around Australia and potentially the Asia-Pacific region. And then the third pillar of the company's business strategy, where I come in, is to develop additional sites for Cobalt Blue in Australia and around the world through the reprocessing of mine waste. So our waste streams project is standalone and on a global scale, so it doesn't necessarily rely on infrastructure in Australia, but if the opportunity is there, then of course we'll feed into that too. A little bit of flow sheet, which is all new to me because I'm an exploration geologist by background, but I'm learning very, very hard about metallurgy. So it's just geochemistry really, which is good. The Cobalt Blue process lends itself to the mine waste application because of the very, very strong focus on sulfides, particularly pyrite, which tend to be concentrated in waste stockpiles such as tailings dams. So this is our flow sheet here as it would be applied in a mine waste scenario. So the one that you might see on our website for the Broken Hill project has a lot more detail around it because it's very specific to that site, whereas this is taking feed from a tailings dam or other waste. So the sulphide waste is generated through previous or ongoing mining activity. Maybe, can you see my cursor if I wave it on the screen? Cool. So we've got some sort of source here, and then we take it off the tailings dam, send it through to concentration step. So that's here. It's already crushed, so we don't actually need to crush it too much, but we do, at Broken Hill, we do gravity separation. So we're sort of assuming that we could do something similar at other sites. And then we make it a pyrite concentrate. We then feed that through a calcine stage where we are converting the pyrite into pyrrhotite down here. And as part of that, we also make elemental sulphur as a byproduct. And just as a little side note, Australia is a net importer of elemental sulphur and sulfuric acid. So for us, it's not a hugely valuable product in and of itself, but if we have a domestic source rather than having to import something that's not really worth a lot, then that's obviously a much better scenario for everybody, for downstream users. Okay, so we've made our elemental sulphur, we've done the calcining, we've turned it into pyrrhotite, and we go through a series of leach steps. We also produce elemental sulphur as well as an iron-rich residue. And then we make out of that leach, we make the final mixed hydroxide precipitate, containing both cobalt and nickel, and then we will refine that to make intermediate cobalt or nickel sulfate via the refinery. So that is metallurgy 101. So just, I'm a geologist, I'm going to visualise that a little bit better. Here are our final products. So the mixed hydroxide precipitate, which contains both nickel and cobalt, is the green stuff on the left. And we can then refine that at the refinery to cobalt and nickel sulfate, which is a step further along that the material needs to be to go into a battery. And that's the reddish stuff. And then our byproduct is elemental sulphur, which can be prilled, as we've shown here. And prilling it just means you turn it into little pea-sized balls or even smaller. And then that can be safely stored or stockpiled. It's completely benign. It's not like sulfuric acid, which of course is dangerous if you, I don't know, have a giant set of train wagons that come off their tracks, as happened in 2015 in Queensland. And I think it was carrying nearly 1 million tonnes of sulfuric acid, which then a lot of that escaped out into the environment, which was obviously pretty bad. Whereas this stuff is really safe. You can stick your fingers in it, and you know, if you're stupid, maybe you could lick it, but it's not going to cause environmental damage if there's some kind of accident and it spills. So then that can be used in the fertilizer industry from phosphate deposits, for example. And then that is a good story because then that feeds into supporting action against global food shortage. So our waste streams project aims to generate opportunities for the reprocessing of mine waste to extract these valuable battery minerals, but then also removing the sulphur from the mine site at the same time, or the waste site. The way we sort of working this, that we work with existing operations and incumbent companies to develop collaborative relationships to be able to realise this secondary metal extraction. So we're aiming basically to turn trash into treasure, and we realise, hopefully we will also realise the positive environmental outcomes for the existing sites and then their associated communities. So then that helps to boost the ESG credentials of not only the battery material that we produce, but also the sites and the companies that we partner with. Again, we do this by being collaborative. We have existing collaborations with the Queensland Government and through them, the University of Queensland, and we also have a number of both public and private collaborations with companies to examine mine waste at specific sites and to develop a body of analytical processing data to demonstrate the efficacy of our processing technique across a number of sites, because each one has their own mineralogical and chemical characteristics. So we don't treat it as a black box where this is how we do it and we can't do it any other way. We try and sort of tweak things to be specific to each site. I've got two examples of work that we're doing. One is through the Queensland Government and the University of Queensland collaboration, and this is test work that we've done at the Osborne site in northwest Queensland, and that's an iron oxide copper gold deposit. You can see the tailings facilities in the image there, and the information that I'm showing is with permission from the Geological Survey of Queensland, University of Queensland and Chenova. So I want to thank all of them for allowing me to share the work here. So image of the Osborne tailings on the left, and that image also shows the results of sampling which was performed by the team at the University of Queensland on those tailings dams. And the recovery results of the test work that Cobalt Blue undertook is shown on the right. Again, I'm not a metallurgist. I'm not going to go into the full details of the test work, other than it followed that flow sheet that I talked you through just a moment ago. But do chase me up if you want to know more. I can put you in touch with our metallurgists. But ultimately, the message here is that test work came off pretty well. We achieved 90% recovery of cobalt from the Osborne samples using the Cobalt Blue process, which is the one that I've highlighted with the little green box. And we can publicly demonstrate that, therefore, that this process works on deposits other than the Broken Hill project, because that's what we want to do. We want to show that, okay, we've got this one down in New South Wales, but we can actually apply this to a whole range of other deposit styles, mineralogy, geochemistry, and that sort of thing. But the key is the presence of pyrite. So this is really good news for other pyrite-rich tailings facilities, whether they're in Australia or elsewhere around the world. But I do want to emphasise that this work was done as a research project with Queensland Government and the University of Queensland, so it doesn't constitute a commercial arrangement with Chenova. However, the sorts of outcomes that we're hoping to achieve with this program, it doesn't have to be focused on contained metal value. So sometimes the value of a path of action is actually in reducing historical harm or the potential for future harm. And that's what we have in this example here. So earlier this year, Cobalt Blue announced a test work collaboration with Hudbay Minerals in Canada to look at the potential for Cobalt Blue's process to extract elemental sulphur from mine tailings at Flin Flon, which is in Manitoba. The mine there has actually closed, but only sort of in the last 18 months, 2 years. But it operated in various guises for nearly 100 years. And it produced mainly copper and zinc. There's actually not a lot of cobalt there. It's a copper, zinc, silver mine. But what remains is the huge tailings dam, which you can see in this picture here, and it has approximately 85 million tonnes of sulphur-bearing waste. And associated with that site, which is now closed, it's not generating further income for the company, but it does have a significant and very long-lived environmental bond, which is the same sort of thing that we have with sites here in Australia. So by demonstrating that we can extract elemental sulphur, which again is a byproduct of our patented process, we can show the potential for de-sulfidisation of this style of acid-forming legacy site worldwide. You can see in this image as well, there's a town, it's like a lot of other Australian mining towns, except it's in Canada and it's a lot colder. So there's a town right here. This is the town of Flin Flon on this little image. So it's a really old site, and the town has just sort of grown up around the edges of that. So people living very, very close to this nasty sort of, site with a lot of environmental legacy. So by reprocessing this material, we can generate some valuable copper, zinc and silver and whatever else is in the tailings dam as credits, but we're also going to produce the sulphur prill, which is those little yellow balls that I showed you before. That is a saleable product. So also, generating value, but at the same time reducing the site's environmental liability. So in some ways, it's a completely different way of looking at a business proposition, because we're reducing the risk. And therefore reducing the amount of that bond that's tied up that the company can't access for other investments or other things. And then coming back to Australia, this map shows the Australian operating and legacy mines, and it's coloured by commodity. And I couldn't quite get the original mine waste atlas on GA's site to then show me this kind of thing. But I just wanted to demonstrate that not one of these, they're coloured by commodity. So, red is iron ore, yellow is gold and silver. The bluey colours are base metals, including copper, lead and zinc. And then the green is battery metals, which is nickel, cobalt, manganese, a bunch of other stuff. So, the idea is to look at this and say, okay, this is broadly where the gold is, this is where the copper is, the greys, coal, that kind of thing. But not one of these deposits will have been purely gold or purely copper or purely zinc and so on. So, Cobalt Blue, the name already tells you we're interested in cobalt. So then knowing that there's very little data on the waste for all these sites, knowing the characteristics of key deposit types then really helps us to build a model to predict which sites are most likely to have cobalt or nickel insert, and that cobalt or nickel is in need of rescuing from a dirty great tailings pile. Somebody used the word rescuing critical minerals I think it was at IMARC, and I just thought it was so cool. So by being a bit predictive, we can narrow the search space from over 3,500 sites to a few tens of sites by understanding the characteristics of the original deposit and then predicting what might have gone into the waste. A lot of the data that we need to characterise waste is still in the early stages of being collected. Anita Pavaka-Fox's group at the University of Queensland is leading the way with that data collection, helped by all the state surveys and Geoscience Australia. But a lot of it's still being collected. It's not public yet. What we can't do is predict things like cobalt content in waste based on the historical production data of the original mine, which would have been very focused on copper, nickel, whatever the focus of that original site was, because in 99% of cases, there was never a formal cobalt resource on that site, and there was certainly no production, processing or recovery data. So we've got no starting point, so therefore there's no way to predict what the geochemistry of the waste is outside of the original commodity that was the focus of that mine site. But the data is definitely slowly growing, which is awesome, and that's a great thing for having a more efficient and circular mining industry in Australia. So our philosophy, of course, in collaboration with host companies or with incumbent companies, is to achieve simultaneous valorisation and remediation of mine waste sites. With the right partnerships, we hope to demonstrate domestic battery metal production, generating a local and ethical supply of critical raw materials for the Australian battery industry, which, you know, is still in its infancy, but growing all the time. We hear governments talking about battery hubs and things all the time. So at the same time as doing that, we can produce the elemental sulphur, which feeds into the fertiliser industry, amongst others. Because we do that, we're generating positive environmental outcomes for problematic mine sites. We are in the process of putting together collaborators and partners now, with Hudbay's Flin Flon tailings facility being the first cab off the rank publicly. So there's a lot going on, and I'm going to leave it there.